Here is a physics question with a demo. So I'm going to start off with, I've already prepared these two pieces of tape. This is two pieces of clear tape and they're stuck together. And it turns out when you pull them apart, one becomes positively charged, one becomes negatively charged. Let's just assume the top one's positively charged. I'm going to pull it apart, I'm going to save the top one, I'm going to make another top one. So I'm going to have two positively charged tapes. So be careful, they do stick to you when you pull them apart. So here we go. I'm only going to keep the top one. I'm going to put it to the side and make another one. Throw that one away. Put this right there. And then make another one. It sticks to everything. Goodness. Okay, here's my second piece. I'm only going to save the top piece. You got to kind of go fast because they don't stay charged forever. They interact with the water in the air. So there's my second piece. Now I can take my two pieces carefully and hold them near each other, and you can see they repel. And so I want to use the angle that they repel to estimate the charge on the tape. That is pretty cool, right? You see they're not repelling, and then they're repelling. And it doesn't matter if you turn them around, they still repel. They just don't bend as well. There you go. Pretty cool, right? Okay, now you got to get rid of the tape. So let's turn this into a physics problem. And I just picked some values here that may or may not be exactly like the one that we saw because I don't really care about the value. So imagine that I have just 2 point masses hanging on the end of strings because it's really hard to, although the tape is charged, it's hard to deal with that whole tape. So let's just say that there's 2 charges Q, length L, and they both hang at an angle theta, and I want to find the charge on the tape. I picked some values for the mass, 0.1 gram, not very much, the angle of 10 degrees, and the length of the string is 10 centimeters or 0.1 meters. I guess I should put that up here because I'm going to erase this stuff. Let's see, right here. So let's say M 0.1 grams, not kilograms. Theta is 10 degrees. L is 0.1 meter. Okay, so I know that if they're at rest, then the net force on each charge is 0. So let's draw a force diagram for this mass right here. So I have the electric force pushing them apart, the Coulomb force. I'll call that Fc for Coulomb force. And then I have a downward gravitational force. I'll write that as mg. And the net force has to be 0, so there's one other force, and it's the tension of that string pulling this way. So those forces have to add up to 0. Now, I can pick, this is my x-axis, this is my y-axis, and then if this is the angle theta, then that is also the angle theta. You can just use a little geometry, right? Because I have corresponding angles, or whatever that's called in geometry. You know what I'm talking about. Okay. So I want to find the charge, and that charge is in here, in that force right there. Remember, the Coulomb force, Fc, is K Q1 Q2 over R squared. That's the magnitude of that, where K is a constant. So I actually can find R. This is R. So this distance from here to there is R over 2. And this is a right triangle. So I can say R over 2 is equal to the opposite side of this angle theta. So that would be L sine theta. Because remember, sine theta is opposite over hypotenuse. So the opposite is R over 2. The hypotenuse is L. So this tells me that R is equal to 2L sine theta. So I can put that in there. I'm trying to find these two charges. I'm going to assume they're the same value. So this is actually Q squared, right? They have the same charge. So, but if I can find an expression for that force, I can find those charges, but how do I find the force? Well, let's just use our normal Newton's second law. F net in the x direction is 0, and that's going to be this force, Fc, the Coulomb force, and then a component of the tension, right? So part of that tension, this side up here, pushes in the negative x direction. That's going to be negative t sine theta. Now remember, you got to look at your picture. You can't just say x component's cosine. That's not always true. Because I'm measuring from the y angle, the x component's actually sine. And so I know 0, I know theta, but I don't know t. So let's look at the y direction and see if we can find t. F net y is equal to 0 because it's not accelerating. And here the y component of the tension is going to be t cosine theta, because it's the adjacent side, minus mg. So from this I can actually solve for t. And I'm running out of room for some reason. T, okay, fits, equals mg divided by the cosine of theta. Right, so it's add mg to both sides divided by cosine theta. Okay, so now I can go back over here and start plugging in some stuff. Let's put this up here because we need that. R is 2L sine theta. I need that. And I can remember this Coulomb equation. I think my problem is I put my picture right here. It's kind of in the way. But that's fine. You make mistakes, right? That's why it's a chalkboard. I could erase. So let's go over here. FC is T sine theta. I get that by just adding T sine theta to both sides. I solve for FC. I'm going to substitute in my value for T. FC is going to be T, which is mg over cosine theta sine theta. Now, sine theta over cosine theta is equal to the tangent. You don't have to do that, but I'm going to put that. So it's going to be mg tangent theta. So that's the value of my Coulomb force. Now let's use that with the Coulomb force equation to solve for the charge. So I'm going to take this, mg tangent theta. I guess I could do it higher. Yeah. Mg tangent theta is the Coulomb force, which is k q squared over r squared. But remember, r squared is this. So I get mg tangent theta k q squared over r squared. So it's going to be 2 squared, which is 4, L squared sine squared theta. So 4 L squared sine squared theta. Now, yes, that looks messy, and you're like, where do we put in the numbers? You can put the numbers in at any point. I don't like to put in the numbers because I don't really care about the numbers. But I'm going to put the numbers in, but let me first just solve for Q. So let's multiply both sides by this, and I get mg tangent theta 4L squared sine squared theta, and then I'm going to divide by k, and that's equal to q squared. So q is equal to the square root. Actually, I can pull that 4L squared sine squared theta out. So I get 2L sine theta times the square root of mg tangent theta over k. Now we have to put in our values. So I like to write it out. So q is equal to 2 times L, which is 0.1, times sine of 10 times the square root of the mass, 0.1 grams. Now, I have to convert that to kilograms, so I have to divide that by 1,000. So I'm going to say 0.1 times 10 to the negative third. And then I have G, 9.8, it's the gravitational constant. And then I have tangent of 10 degrees divided by K, 8.99 times 10 to the 9th. That's that Coulomb constant. So now we're just going to have to put it in our calculator. I'm going to use my calculator. Make sure your calculator is in degrees mode, which mine is in degrees, I think. Okay, I'm not a calculator expert. Okay, I'm going to stand right here so I can see the light a little bit better. 2 enter 0.1 times 10 sine, okay, that's good, times, and then I have 0.1 times 10 to the negative third, enter 9.8 times 10 tangent times 8.99 times 10 to the 9 divided by square root times. And I get, ooh, that's not the chocolate one. There it is. And I get Q equals 4.81 times 10 to the negative 9th coulombs. That's it. So it looks like a daunting problem, but if you just work through it step by step, it's not that bad.